The last section of Chapter 2 involves rational functions, which is a fancy way of saying you've got fractions that have variables in them. I want to talk about how we graph those today and look at some of the important features of rational functions. We've talked about this basic rational function, y equals 1 over x, before. We just call it the reciprocal function. Quick reminder of what that graph looks like. If you start thinking about making an xy table, plugging in values in here, you'll notice right away that we can't use every single x value. We have a domain restriction where x can't be 0, right? We don't have a value there, which means we're not going to have a point on our graph there. Think about these other values. If we plugged in -2 for x, we have -1/2 for y. Here's -1, 1, 1/2. As we plot those points, hopefully remember what that graph kind of looks like, where we have points in the first and the third quadrants. And the bigger x gets, the closer this graph gets to the x-axis. So if I were to say make x equal 1,000, well, y would be 1 over 1,000. That's really, really close to 0. So our graph starts to approach 0. And then over here, as we put in fractional values, like if I made x a half, well, y would be 2. So I have a point here, and this graph comes up like this, and then does the same thing in quadrant 3. This is an odd function. It has origin symmetry. If you replace the x with a negative x, we get the opposite of the original function. And so we have that origin symmetry there. That's the graph of our reciprocal function, the most basic of our rational functions. And I do want to talk about the asymptotes of this graph. Remember, asymptotes, we've defined them in the past as lines that our function approaches but never quite reaches. In this case, the x-axis is a horizontal asymptote. We say the equation of that horizontal asymptote is y equals 0. We also have a vertical asymptote in this case, the x-axis. There's a vertical asymptote. Remember, vertical lines are x equals, so x equals 0 is the equation of the y-axis. Those are two guiding lines that help us sketch our graphs. Later on in this section, we might look at some more advanced graphs, and having those asymptotes there are kind of serve as a nice guideline for us. Okay, so that's our basic y equals 1 over x. While I'm here, let me mention what would happen if we change this to 1 over x squared instead of 1 over x. The biggest impact would be that all the outputs would have to be positive. It doesn't matter what x value I plug in there now. And let me do a new values in our table for 1 over x squared. If I plug -2 in for x, this becomes positive 1/4. Positive 1. Still no value when x is 0. Our domain remains everything that's not equal to 0 for x. And here 1 and 1/4. So we get the same types of values that we're approaching. 1 over x squared here. You think about this point here, and then if, when x is 2, we get 1/4. We're still approaching 0. It actually approaches 0 a little more quickly. Both x equals 0 and y equals 0. But we won't have this graph in the third quadrant because we can't get negative outputs. We'll get these values up here in quadrant 2. We'll have an even function this time. If you replace x with negative x here, negative x squared, it's right back to 1 over x squared. So you have an even function. There's y-axis symmetry on our graph. So both of the asymptotes there would have the same equations. Y equals 0 for the horizontal, x equals 0 for the vertical. So there's a couple basic rational functions. Just like any other function, rational functions, if you know your transformations, good old purple chart, if you know your transformations, you can graph some of these fairly easily. 1 over x plus 3, well, think about what that plus 3 would do to your graph. I've got some function, I'm adding 3 to it, it's going to move my graph up 3. So I can take that original graph of 1 over x, think about what that would have looked like from the last board. That whole thing moves up 3 units. including that horizontal asymptote will slide up 3 as well. So we'll now have a horizontal asymptote, HA for short, at y equals 3. Our vertical asymptote, since we're only sliding up, that's not going to affect my vertical asymptote. It was x equals 0 before. If we slide it up, it's still x equals 0. So here's a vertical asymptote, x equals 0. Then we can sketch that basic shape back in, using that y equals 3 and that x equals 0 as guidelines to help me sketch that in. If you need to define x-intercepts or y-intercepts, here in this case you can see there's an x-intercept now. You could make y equals 0 and solve this for x. I think you get negative 1/3 for x, and that would be your x-intercept. If that minus 4 is inside of our rational function, like it is over here in the pink one, that minus 4 is going to move our graph to the right. So move to the right 4. Now that vertical asymptote will slide to the right as well. Vertical asymptote will be at x equals 4. Horizontal asymptote, if you slide a horizontal line to the right, it's still the same horizontal line. So a horizontal asymptote remains y equals 0. In this case, sketch in your graph. So the reason those transformations are so important is that every time we see a new function, those transformations will work the same way. Once we know the shape, what we call that parent function, the basic shape of the graph, then our transformations will help us move around the coordinate plane. So we'll use transformations to our advantage. In general, if we want to try to find where these vertical asymptotes are before I go to the next board, you'll notice here your vertical asymptote is still at 0 because we're dividing by 0. That'd be undefined. We wouldn't have an output there. Here our vertical asymptote is 4. We'll notice 4 minus 4 would make our denominator 0 again, therefore not give us an output. And every time we're looking for a vertical asymptote, we can find that vertical asymptote by making the denominator equal to 0. There's a little except for here that I'm going to mention in a second. So as I look at a function, if I want to know where the vertical asymptotes are, like here, finding the vertical asymptotes here, this will happen anywhere that the denominator equals 0. So I take my denominator, set it equal to 0, and solve. Take out my common factor. Keep on breaking this down. This graph actually has 3 different vertical asymptotes, which is kind of a strange thing to think about at first. X equals 0, x equals 2, x equals 4. There are actually 3 different vertical asymptotes on this graph. Actually, you know what? Why don't you, in your calculator now, go ahead and graph this function just so you can get a look at what a different kind of rational function might look like. Go ahead, okay, pause that for a second. Just, yeah, over on the computer there. Will you just hit pause for me? Thank you. All right. Great. Oh, you graphed it, right? Okay. So you graphed it and you saw the 3 different vertical asymptotes there. All right. You always want to look for your denominator to equal to 0 to find a vertical asymptote unless your numerator equals 0 for that same value. So you compare this one over here. It's the same denominator, so my first thought would be when this denominator equals 0, I know my 3 vertical asymptotes. However, notice that 2 would also make the numerator equal to 0. If both the numerator and the denominator equal 0, that won't be a vertical asymptote. So this equation, this graph will only have 2 different vertical asymptotes, x equals 0 and x equals 4. What happens is that when x equals 2, you certainly have a break in your domain. You can't divide by 0. We know that's one of the things we look for when we're looking for domain. But if the numerator and the denominator are both 0, if you've got a 0 divided by a 0, it won't be a vertical asymptote. It'll actually just be a hole in the graph. And so again, put this in your calculator and take a look at what that graph looks like. You won't be able to see the hole at first. But if you go to the table and try to see what happens when x equals 2, you'll see there isn't a value there. It doesn't look like it's discontinuous. It looks like it goes through 2 because the calculator doesn't do a great job of showing that. But if you look at the table, or even if you go on the graph and try to find the value when x equals 2, you won't get a y value. Just leave it blank. It'll say error in the table. There isn't a value there, but notice there's not a vertical asymptote either. There's a hole in the graph there. So this would only have 2 different vertical asymptotes. So always look for your denominator to be 0, but take a look at your numerator, and if your numerator equals 0 at the same place, that won't be a vertical asymptote. All right, so that's vertical asymptotes. Horizontal asymptotes, the last thing I want to talk about. We've seen graphs have 1 horizontal asymptote, and the majority of graphs will just have 1. Next year in calculus, we'll see the occasional graph that might have 2 different horizontal asymptotes. Horizontal asymptotes are what happen on your graph when x approaches infinity or when x approaches negative infinity. You know, we saw that happen in the 1 over x graph. As you approached infinity, that function was heading towards 0. Even if you approach negative infinity, the function was heading towards 0 this way also. We had 2 different, one asymptote coming from either direction as we approached infinity or negative infinity. So I just want to kind of explore a few different functions and their horizontal asymptotes, and then we're going to kind of make some conclusions from there. So I'm going to start with a fairly basic reciprocal function. If we made x approach infinity here, if we made x get really, really big, so think about putting like 1,000,000 in for x or 1,000,000,000 in for x. Well, that y value would be 3 divided by 1,000,000, 3 divided by 1,000,000,000. That'd be really, really small. So the bigger we make x here, as x approaches infinity, this function will approach 0. The y values will approach 0. So the horizontal asymptote here would be y equals 0. Notice that's also the case as x approaches negative infinity. If I made this 3 over negative 1,000,000 or 3 over negative 1,000,000,000, that's a tiny, tiny fraction. It's a little bit negative, but it's a tiny, tiny fraction. It's getting closer to 0. Now, what if I change that and said instead of 3 over x, 3 over x squared instead? What would happen if you made x really, really big? Well, it would still make the denominator really, really big. In fact, the denominator would get even bigger faster. 1,000,000 squared, 1,000,000,000 squared, and these are enormous numbers. You 3 divided by that big giant number, that fraction is approaching 0 again. So once again, this graph would have the same horizontal asymptote, y equals 0. Notice these are just in the family of the 1 over x and the 1 over x squared graphs that we saw on the first board. All right. Well, so let me try to jazz it up a little bit. What if I turn this into y equals 3 over x squared plus 1? Well, I just made the bottom bigger. Now it's even 1 more. And really, who cares about the plus 1 if you've got 1,000,000 or 1,000,000,000 squared down there? That plus 1's not really going to do much to your graph. So this graph, again, would have the same horizontal asymptote of y equals 0. So notice all 3 of these functions, they'll look different on the graph, but each of them will say I have the same horizontal asymptote at y equals 0. Let's see, what should I say next? How about, I hope you can see this one. Let me go see if you can see this. Oh yeah, 3x over x squared plus 1. Well, now what happens as x gets really, really big? What happens at the top? Gets big. What happens at the bottom? It also gets big. So both the top and the bottom are heading toward infinity. Which one's getting bigger faster, though? The bottom's getting bigger faster. 3 times 1,000,000 for x would be pretty big, but not as big as 1,000,000 squared. That squared on the bottom is going to make the bottom grow faster. And if the bottom's growing faster in a fraction, that fraction's value is going to approach 0. Yes, these both get bigger, but the bottom gets bigger faster. And so once again, We have that same x-axis, y equals 0, as a horizontal asymptote. All right? Well, now, let's see. Is there something I can give you that wouldn't? It's not always going to be y equals 0. So, what if I do this? I say x cubed over x squared plus 1. What happens as x approaches infinity? Well, both the top and the bottom are getting bigger, but which one's growing faster now? Right? X cubed is going to get bigger faster than x squared. Cubing a big number makes it really, really, really big, as opposed to squaring a big number, which just makes it really big. So the numerator is growing faster than the denominator here. So as the numerator grows larger than the denominator, that fraction's top heavy. It's getting bigger and bigger and bigger. Makes that fraction's values get bigger and bigger and bigger and bigger. So as this happens, y is going to get bigger and bigger and bigger. So as x approaches infinity here, go back to end behavior, as x approaches infinity, y also approaches infinity. So instead of this graph approaching any sort of value, y just keeps getting bigger and bigger and bigger, and therefore there is no horizontal asymptote. So in this equation, there is no horizontal asymptote, because the top is growing faster than the bottom. There's no y value that we're approaching there, okay? Well, I guess that leaves something like this. Let's say, what if I made 2x cubed on top and x cubed, say, plus 1 on the bottom? Well, now the top and the bottom are both growing again. They're growing at a proportional rate. We don't really care about that plus 1. You know, if I'm approaching infinity with x, a billion cubed plus 1 is pretty much the same as a billion cubed. You're not really going to care about that plus 1. So what's happening here is both the numerator and the denominator are growing at a proportional rate because they've got the same exponent on both the top and the bottom. The degrees on the top and the bottom are the same. In a case like this, we have to go to the coefficients of those terms. Or, as I said, this plus 1 really, we don't really care even about that plus 1. So now we've got 2x cubed on top, we've got 1x cubed on the bottom. As x gets bigger and bigger and bigger here, and you can explore this if you want by just plugging in an x value. You know, put in an x value like 1,000,000 or something here, and figure out what this fraction equals. If you're going to do that in the calculator, don't forget to put that in parentheses. What you'll find is that as x gets bigger and bigger and bigger here, the y values of this approach the value of 2. So the horizontal asymptote here would be at y equals 2. Okay. And again, you know, if you want to look at that in your calculator to kind of convince yourself of that, you can. What it comes down to is, since the plus 1 doesn't really matter, these two are growing at a similar rate, but that rate is dictated by the coefficients. We've got an x cubed on the bottom, we've got twice an x cubed on top. So it's like a 2x cubed on top over 1x cubed on the bottom. That 2 over 1 there is going to tell you what your horizontal asymptote looks like. Right? So a lot of different examples of horizontal asymptotes there. I want to wrap this up by trying to summarize what we've seen with these horizontal asymptotes. Here we go. To find where the horizontal asymptote is for your rational function, you want to compare the degrees in the numerator and the denominator. What's the largest exponent on top? What's the largest exponent on the bottom? Those are the only values, the only terms that matter. Any smaller degrees will sort of become unimportant as you make x bigger and bigger and bigger. If you've got a bigger exponent on top, that means the top's going to grow faster than the bottom. The y value is going to approach infinity like we saw in the example here, or maybe negative infinity depending on signs of things. But the key is y just continues to grow, or y just continues to get smaller and smaller and more negative, and therefore there is no horizontal asymptote. That's therefore, remember. So no horizontal asymptote if you've got a bigger exponent on top. If you've got a bigger exponent on the bottom, well, now the y values approach 0. The top grows slower than the bottom. Bottom's growing faster, so that fraction gets smaller and smaller and smaller and approaches 0. So therefore, you'd have a horizontal asymptote at y equals 0, the x-axis. We saw that with 1 over x and 1 over x squared and 3 over x and 3 over x squared plus 1 and so on. And then finally, if the degrees on the top and the bottom are equal, we compare the coefficients of those terms that have the largest exponents. So this example here, we want the equation of the horizontal asymptote for this function. The only terms that matter are the largest exponent on top and the largest exponent on the bottom. None of this makes any difference for our asymptote. It might affect the shape of our graph or intercepts or vertical asymptotes maybe if we set the bottom equal to 0. But for horizontal asymptotes, we're just looking at these first terms. Since it's a tie, since the degree is the same on both the top and the bottom, we look at the coefficients of those two terms. And 2 over 5, y equals 2/5 is the equation of your horizontal asymptote, right? So there's a summary of how to find horizontal asymptotes for all your rational functions. As you look at the problems in this section, hopefully you'll be able to sketch some graphs, find some vertical and horizontal asymptotes, and graph accordingly.